So in this lecture, let us take a quick review of what we have studied earlier. Okay. So we studied about different types of crystals. Okay. And like the face centered, body centered, and the simple cubic, etc. We read about the reciprocal lattice. So what did we study? So we studied that these crystals can be made just by using translation of three vectors, and those vectors were a1, a2, and a3. So what you can do with these vectors is, if you go on using these vectors, for example in 2D, so consider I make a vector. So this is say a1, okay, and this vector is a2. So if I continue using a1 and a2 in the space, I can make the entire lattice. For example, so if I just go on, so go on putting this, you see what I'm doing? I'm just continuing using a1 and a2 vector in the entire space, and look how I'm spanning the entire 2D crystal just by using two vectors a1 and a2. So this is the idea behind the lattice vectors. So like a1 and a2 can span the entire 2D lattice. Okay, so let me write. So my this vector in 2D, this was my a1, okay, and here the below small one was my a2. Okay, so you can see here that like I can span the entire 2D space using a1 and a2. Similarly, I can span the entire 3D space using a1, a2, and a3. Now we were not happy. The scientists or the X-ray diffraction crystallographers were not happy, and they found a Fourier space, and they defined, they said instead of using a1, use b1, okay, b2, and b3. So like a1, a2, and a3, when we repeat them, they create a crystal lattice. Similarly, we have b1, b2, and b3. When we repeat them in space, they will span another crystal lattice, and that crystal lattice is called as reciprocal lattice. Now we will now take a look at how they actually look. Okay, before that, let me remind you how a1, a2, a3 were related with b1, b2, and b3. This was the relation how these two spaces are related. Now we'll see something quite interesting. Now we'll actually see this in action. Okay, let us continue. So you see, let us start with 2D. Okay, before coming to 3D, let us start with 2D. Consider this particular diagram. Consider this particular diagram here. Agreed. So just let me remove all this. And let me bring the diagram here then. So look at the diagram. Okay, so what do you see from the diagram? If you look at the diagram closely, let me draw it in another better place. Okay, so if you look at the diagram closely, you find something very interesting. You see that we have a real lattice. See, this is a real lattice. So this is my a1. So let me write a1, and this, the red one, okay, this is my a2. So let me write this as a2. we know that in 2D A1 and A2 will span the real lattice. So let me make it all red so that you understand that A1 and A2 they span the real crystal lattice. Okay, now what was the plan? Now we found that by using the formula we can say or we can find two other vectors related to A1 and A2. So I mean, so look at this 2D crystal. This 2D crystal was also spanned by using A1 and A2. So they said that instead of using A1 and A2, okay, you can directly go to reciprocal space and construct the reciprocal crystal by using B1 and B2. Now question is how the reciprocal crystal is gonna look. Let me use blue violet. Look at this graph. So this is my B1, this is my B1, and this part is my B2. So we can see that the crystal lattice A1 and A2 has a reciprocal lattice. The red part, all the red part or the red lines that you see, they all represent the lattice vectors, and using that lattice vector the entire red is the real crystal lattice in the real space, where A1 and A2 are the real space lattice vectors. And everything that you see in green or violet, okay, if you see everything that you see in green, the green is the reciprocal lattice of the real red crystal lattice, and the green is the reciprocal lattice, and that reciprocal lattice has two vectors b1 and b2, and using that two vectors b1 and b2 we can span the entire reciprocal lattice crystal. Okay, the same case, the like you use A1 and A2 to span the entire crystal in real space. Similarly, for a real crystal, that is a equivalent reciprocal crystal, and that reciprocal crystal of the real crystal has vectors b1 and b2, and that b1 and b2 can span the entire reciprocal space. So this is, so the green one is how the reciprocal crystal, reciprocal 2D crystal. So the green one is a reciprocal 2D crystal of the real red crystal. The red one is a real crystal and the green one is a reciprocal 2D crystal of the red one. Let us look at 3D. So let us come to the 3D. Here is a 3D diagram for the reciprocal lattice vector. So 3D diagram, you see something interesting happening here. Okay, so this is the 3D diagram. You see in 3D diagram, you have three vectors. So given ABC, so let me use our terminology. Our terminology was the real vectors are A1. So this will be A2, and this will be A3. So the black one that you see, the black diagram represents the real crystal. Okay, so this black diagram or the black block that you see is our real crystal. By a real crystal I mean the direct crystal. Okay, and we know that by using this relation, so you remember this relation. Okay, by using this relation we can go from real vectors a1 a2 a3 to reciprocal vectors b1 b2 and b3. Now this b1 b2 and b3 will span the reciprocal lattice. So like a1 a2 and a3 has spanned the real crystal, the black one, the real 3D crystal, and this crystal, so if I repeat this black crystal again and again on space, I will get a entire crystal. This crystal, this basic crystal has a reciprocal equivalent, and the green one can be shown have, so what was our terminology? Using three vectors b1, this will be b2, and this part will be b3. So the green one contains three vectors b1, b2 and b3, and b1, b2 and b3 are the basic lattice vectors of the reciprocal lattice. So this green diagram is the reciprocal crystal of the real crystal. Okay, so now we actually understood the diagram and the mathematics. So what was the mathematics? The mathematics was, by using Fourier transform, we were able to go from real lattice vectors to reciprocal lattice vectors. Now once we have went to reciprocal lattice vector, from these diagrams you can see what reciprocal vectors in the reciprocal space actually look. There is an interesting thing. You see there is a change in size. There is a reason. If you look at our last lecture, in the last lecture you'll mark an interesting thing. You see A1 has a dimension of length, A2 has a dimension of length, A3 has a dimension of length, and B1 has a dimension inverse of length, and the A is below. So if the A is small, B is gonna be large. If the A is gonna be large, B is going to be small. So if you can look at this diagram, look at the 2D diagram. Okay, look at this 2D diagram. A1 is big. You see A1 is a long vector. So the corresponding B1 is small. You can see that. Similarly, A2 is long vector, and accordingly A2 is small vector. You can see it ends here. Okay, A2 is a small vector, and the corresponding B2 is a larger vector. I mean it's a longer vector, because B2 is the reciprocal of A2. You can see from the previous lecture. Okay, so the reciprocal lattice always have a dimension 1 by length. They always have a dimension 1 by length. We can also look at further. So this is the reciprocal lattice vector. This is the real lattice vectors of the simple cubic. Let us look at face center. So for the face center, these A1, A2 and A3, they represent the real lattice vectors, and the corresponding reciprocal vectors are given as b1, b2 and b3. They're given as this. Okay, so similarly you can convert a real crystal into a reciprocal crystal. This is the reciprocal crystal. So instead of doing work with the real crystal, we can make the reciprocal crystal with respect to the real crystal, and we can do our entire work in the reciprocal crystal. Now the question is, what work are we talking of in the reciprocal crystal? And whatever the work is we are doing in the reciprocal crystal, does the reciprocal crystal simplify our work? Okay, so that's our question. So question is, what work does reciprocal lattice simplifies? So the entire story begins like this. So now comes the most important part that you must focus on. Agreed? Most important part. So what happened, how it was happened, and what led to the discovery of reciprocal lattice vector, we'll discuss in detail. Okay, let us continue. So the entire story started with X-ray diffraction. Okay, so what happened with the X-ray diffraction? You have learned diffraction pattern in your +2 physics, where you have learned about the diffraction of light by a slit. Okay, but here we are talking of diffraction of X-rays by using crystals. Okay, now question is, why use X-rays? Because you remember the phenomenon, the rule that says that if the slit is if the width of the slit is comparable to the wavelength of light, only then there will be a diffraction pattern. For the crystals, there is some parameter called as the distance between planes. So we'll discuss that later on. There is some parameter which is so small that crystals can only scatter or diffract the X-rays. They cannot scatter or diffract the light rays that we studied in our +2 physics. So the story started like this. So we have crystals. Okay, so you see these blue points. These blue points are nothing but atoms which are arranged in a periodic manner. So this is a 2D crystal. Although the experiment was done with 3D, so the explanation can also be explained by using 2D. So what happens here is, you see the red line. The red lines are the incident lines or the incident wave or the incident X-rays. They fall on the crystals. I mean, they hit the atoms of the crystals and they get deviated. And okay, and what happens is, this light, the upper part of the incident light and the lower part of the incident light, okay, they interfere here and they produce a interference pattern. So let us look at the pattern. So this diagram shows the pattern. What happened here is, at particular angles they found a high intensity of X-ray. So when you have high intensity of X-ray, that shows that there has been some interference. This type of constructive interference can only happen in your either interference or diffraction of light. Similarly, so it was seen that the interference and diffraction, the constructive interference of X-rays was found in this type of experimental setup. I mean, when you use X-ray on crystals, the result is you get X-rays that are either destructively interfered or constructively interfered. It is so when you put X-ray on crystal, it is like when you put light on this slit. Okay, the moment it passes through the slit, you have a pattern, a high intensity and low intensity pattern that you call as a diffraction pattern. Similarly, when you put X-ray on crystals, the result that you get on the screen is also a high intensity and low intensity pattern. And that I also that I described here. The presence of the maximas confirmed that there has been some constructive interference. The presence of the maxima confirms there has to be some constructive interference. So now, based on this experiment, to explain the graph, to explain the intensity graph, we had to do something. Bragg first gave the idea that how the entire thing is actually functioning. He said that when the X-ray light is incident on the crystal, okay, the crystal behaves as if it is not periodic collection of atoms, but the crystal behaves as if it is a collection of planes. So this is quite amazing and very weird. So how does the atom know that, okay, when X-ray is gonna fall on us, we are all going to combine with each other and we will behave like a plane? So this is something very weird, but this assumption that crystal atoms, they behave like plane, worked very well. So Bragg assumed that when X-ray falls on the crystal is a collection of planes. So you have to assume crystal is a collection of planes. Now this is very confusing. You would ask that, but crystal is a collection of just atoms. So where does the plane come from? So Bragg said that these atoms that forms the crystal, so when X-ray falls on them, these atoms, they behave as planes. They behave as planes. I know it's very weird, but it's true. They behave as planes. It is as weird as the wave particle duality in quantum mechanics. Okay, so then what happened, based on the assumption that crystal is nothing but a collection of planes, okay, Bragg found out a formula. So this formula is very easy to derive. So what is the idea behind constructive interference? So you need the path difference between two interfering light to be equals to n lambda. Only when the path difference between two light is n lambda, you will have a constructive interference. So we need to find the path difference between light number 1 and light number 2. If you look at it carefully, you can find the hint for path difference at this position. You can find the hint for path difference at this position. So what's the hint? You see, the light number 2 is covering an extra distance than the light number 1, and that extra distance is, if the spacing between these two planes is d, then there is a d sine theta here and there is a d sine theta here. Okay, so both this d sine theta, so this is a d sine theta and this is a d sine theta. You see, let me make it yellow. So look at the yellow color. This is a d sine theta and this is a d sine theta. Okay, so both d sine theta was the extra path that the X-ray number 2 was traveling. So what is the path difference? The path difference is 2d, okay, sine theta. So what was d? D is the spacing between the crystal planes. Okay, as I said earlier, the crystal behaves as if it is a collection of planes, and then we define something called as distance between two planes, which is d. So this is the d we are talking about. So 2d sine theta is equals to n lambda. This was the Bragg's famous formula that described the X-ray diffraction using this simple formula. Okay, and this worked very well. At various values of theta, we actually got the various values of interference intensities. Okay, and this formula was used hugely. You know, there is a very interesting application of these formulas. Just by using a particular lambda of the X-ray is known, and theta, at which angle you are inciding the X-ray. For example, if you are making an X-ray come at an angle theta, this theta is known to you. You can calculate this theta by using this formula. When lambda is already known and theta is already known, and looking at the interference pattern, they were actually able to calculate the distance d between the planes. So you take different types of crystals and you do different types of diffraction experiment on the crystals, and using those diffraction experiment you can actually find the spacings between the planes in the crystal. So consider this is crystal number 1. So consider you have another crystal, that is crystal number 2. Okay, so you do experiment X-ray diffraction on crystal number 1. You can find this by using Bragg's formula. You can find the distance between the planes. You use the X-ray diffraction using crystal number 2 and you can find the distance between the planes in X-ray number 2, that may be greater or smaller than the crystal number 1. So in this way, Bragg's law at that time was a very famous law, by using which we can actually calculate the distance between the parallel planes. Okay, and these parallel planes are the imaginary planes that we assume the crystal is made up of. Agreed? So this solved a lot of problems. Let me give an interesting observation. So another interesting thing came out, that look at this particular diagram. In this particular diagram, what you see, when the X-ray is falling in this angle, the planes are like this. The planes are exactly vertical. Okay, but the same crystal, when your X-ray is falling like this, okay, so the incident is coming from this side and the result is going from that side. Interestingly, these horizontal planes no more exist, and the same crystal behaves as if the plane has been tilted. So this is something very weird, but this is true. So different angle for the crystal may give us either same or different d, that is different values of interplanar distance d. So that's a different concern. Okay, we are not concerned with that. So we are concerned with the formula 2d sine theta is equals to n lambda, that worked very well. Then came a very interesting plan. They said that, hey, let us look at the formula 2d sine theta equals to n lambda, and we can do something with the formula. warning, we are approaching towards the understanding of reciprocal lattice here. So I hope you have patience, so please listen. So the plan was, look at the formula 2d sine theta is equals to n lambda carefully. Okay, remember that d is the distance between the planes that we assume the crystal is made up of. Okay, and they said, hey, something interesting happens if we make some changes. What are the changes? They said that just write sine theta as it is. Okay, so what is lambda? So there is a difference between lambda and d. Okay, be careful, there's a difference between lambda and d. So lambda is wavelength of light and d is the interplanar distance. Agreed. So lambda is the wavelength of light and d is the interplanar distance. Now somebody said that, hey, we can write this equation same as 1 by d. So considering n equals to 1, okay, doesn't matter whether you take n or not. So 1 by d divided by 1 by lambda. This equation served us a very interesting thing. It said that if we do 1 by d and 1 by lambda, then we can consider these things as objects with dimension 1 by length. So 1 by lambda has a dimension 1 by length and 1 by d has a dimension 1 by length. So the idea was, instead of working with d and lambda, let us work with objects that has structure of 1 by length. Okay, now why do we go to 1 by length? Because when we go to reciprocal lattice, so you remember the reciprocal lattice vectors were all 1 by the length, they had the dimension of 1 by length. When we go to the reciprocal lattice vector, the entire diffraction formula that looks this complicated, actually people say even this is complicated equation, the entire diffraction formula will get converted into a so simple formula, which is a formula for simple geometry. So instead of doing the experiment and finding out theta, d and lambda, people used the reciprocal lattice vector, and in the reciprocal lattice vector the diffraction was nothing but geometry. So you satisfy a particular geometry in the reciprocal lattice vector, and using that geometry you can predict whether the diffraction is going to occur or not. So that was a very interesting observation. Okay, so I'll give you a theorem based on that. As I said, so please remember, so the entire invention of reciprocal lattice vector was based on the fact that you can convert the real lattice into reciprocal lattice, and the diffraction formula in the real lattice, which is Bragg's law, which is a bit complicated they say, can be converted into a simple geometrical formula. We'll look ahead how it gets converted into simple geometrical formula. So it gets converted into a simple geometrical formula, and in reciprocal lattice, instead of doing complex Bragg's law formula, the geometry will give you an idea whether diffraction is gonna occur or not. So reciprocal lattice has brought down a formula of 2d sine theta is equals to n lambda into a geometry. Now question is, what geometry? Okay, so let us look further. So you can see here I have drawn. So this was the experiment done in the real space. Okay, now what I did is, this crystal, which was a collection of atoms, okay, and it has basis vector, say this is a vector a1, okay, and this is a vector a2. This vector a1 and a2, when we repeat them in space, we get the entire crystal. So instead of using a1 and a2, I'm making a reciprocal lattice. So in the reciprocal space, this crystal, it's going to look like this. Okay, and the basis vectors in the reciprocal lattice will be b1 and b2. So you can say this one as b1 and this one as b2, or any way you like. Okay, so let me not do it. Now in the reciprocal space, I want to find out what is the condition for diffraction. Okay, so the point is, so you have a reciprocal space. Now bring in the X-ray. So the X-ray says that okay, you incident an X-ray in this direction. So the X-ray has a vector k. So wave vector k. This is the incident wave vector k. Now, so the direction is in this side. Okay. So let me draw a little bit more. So this is the k. That is the incident wave coming in this direction. Now what will happen? Now the reflected wave from here will go in this direction. Okay, so this is the reflected wave, and I can represent this wave as by using a vector, wave vector k dash. Agreed? So this is an extension. This is just an extension. So this can be also written as k, and the vector can be represented as this. Now it is said you join the vector k and k dash. So when you join the vector k and k dash, you get a vector g. And here in the real space, the condition for diffraction was 2d sine theta must be n lambda. And in reciprocal space, the condition for diffraction is that k minus k dash. Remember, k and k dash are just vectors. Okay, if k minus k dash is a vector, is a reciprocal vector in reciprocal space, then we have constructive interference. Okay, let me write the theorem down. So this is the theorem. I'm giving a tick. So the theorem says that in reciprocal space, a diffraction will occur if k minus k dash is a reciprocal vector. Okay, I mean you do k minus k dash, you get a vector, and see if that vector lies in this space or not. If k minus k dash, I mean the k is the incident wave and k dash is the outgoing wave vector. So if you subtract them, if you get a vector which lies in this space, then a constructive interference will occur. If you get a vector that does not lie in this space, then no constructive interference. That's it. Okay, that's it. This is the beauty of reciprocal space. The entire diffraction formula 2d sine theta is equals to n lambda has been converted into simple geometry, or the best geometry is just do k minus k dash, you get a vector, and see if the vector exists in reciprocal space or not. That's all you need to do. This makes life much simpler, and this presents a huge amount of possibility. It says that all those k and k dash vector are possible whose subtraction will give a vector in the lattice space. So this gives a wide range of possibilities than 2d sine theta is equals to n lambda can give. This was the beauty of using reciprocal space. Okay, I hope you understand that. So diffraction has been explained in real space as 2d sine theta is equals to n lambda, and the same diffraction in reciprocal space becomes the theorem that incident wave vector and the outgoing wave vector, if you subtract them, the vector that you get must be a vector in reciprocal space. If that's the thing, then you have a constructive interference. So this is the reason why we invented reciprocal space in the first place. Agreed? So this is how reciprocal space idea comes into form. Now question is, what is, so this is just a general theorem. So what we need to do is we need to write a more accurate formula for the diffraction pattern. Okay, so in reciprocal space, let us write a bit more accurately. So consider there has been an elastic scattering. So by elastic scattering I mean that there has been a diffraction. You see, this is scattering. K is in one direction and the scattered wave k dash is another direction. So this is just nothing but a scattering. So if I assume that this scattering of X-ray is elastic, by elastic I mean there has been no change in the no change in the magnitude of k, then I can write for elastic scattering. So for elastic scattering, what do we have at hand? So it says that the k dash, the magnitude of the k dash vector is same as magnitude of the incoming k vector. So this is the relation that is satisfied for elastic scattering. Now you know very well that the diffraction condition says that the diffraction is only possible when k minus k dash is a vector in reciprocal space. And remember, we were using a sign convention of g to represent any vector in reciprocal space. So what is k? So what is so let me restate a bit. So what I can do is, so instead of writing k, so what I'll do is, let me write k dash minus k. It's the same thing. It's the same thing. Even if I do k dash minus k, it's not going to change. Okay, so k dash minus k must be a vector in reciprocal space. So what is k dash? K dash is k plus g. So when this will be converted in terms of magnitude, what will I have at hand? I will have k dash square must be equals to, so what is k? Okay, so k dash, what is k dash? You can write k dash as g plus k square. Okay, so this relation comes from the diffraction relation. I mean, these relations come from here, and this must be equal to the magnitude of k, that this must be equals to k square. Okay, this is the entire formula for diffraction. Now what? Now let us just do some little bit of mathematics by using this part. Okay, so this part can be written as, so if you do, oh sorry, the square is not here, let me drop this part. The square is here. Okay, a little bit of geometry, just expand this and you will get another condition. The condition is 2 k dot g. So k is the incident wave vector, so let me write vector. Everything is in vector form. K dot g. G is the reciprocal lattice vector of the crystal which you are using for the diffraction experiment, plus the square of reciprocal lattice vector, so plus g square equals 0. So this is the most general case for diffraction. So instead of writing 2d sine theta is equals to n lambda, if this satisfies, if this equation satisfies in reciprocal lattice space, then it indicates a constructive interference, or it indicates that Bragg's law is satisfied. However, this can be also written in a more better form. So more better form says that you can use a minus g. A better form says that this can also be written as 2 k dot g, 2 k dot g equals to g square. Now question is, how can I write this? Let me give you how can I write this. Let me tell you. So this is written based on the fact that if g is a lattice vector, I mean if g is a lattice vector in reciprocal space, then even minus g is a lattice vector in reciprocal space. So for the minus g, this case is satisfied. Okay, so this is another general form of your Bragg's law. So this is also a general form of Bragg's law. Now to convince you that this particular formula that I am writing, that 2 k dot g is equals to g square, I want to convince you that this is nothing but Bragg's diffraction law, that is 2d sine theta is equals to n lambda. So my plan is, how can I derive the Bragg's law from this part? So remember what we are doing, we are studying the entire diffraction in the reciprocal space, and we can see that In reciprocal space, the entire diffraction formula is nothing but just subtraction of vectors and dot product of vectors and square of vectors. It's just that. So easy. It is just a geometry. It's just a geometry in reciprocal space. So now my work is to prove that 2d sine theta is equals to n lambda. The Bragg's law is same as the reciprocal law. I mean is same as this particular law that we are studying here. Okay, that I'm shading this particular law. So let us see.